Assalamualaikum. We now discuss the second topic in this chapter, chapter 7, partial differential equations. So the method we are going to discuss will be Poisson's equation problem. This is a problem. This is a boundary value problem. So the finite difference method will be applied to solve this problem. Okay, so with Poisson's also we should be able to solve something similar called Laplace equation. Okay, so the basic formula for Poisson's equation is this one here, uxx plus uyy is a function of x and y. So that means we will have x and y here. So we are going to discuss a problem involving this domain somewhere here. So this is a boundary value problem where the boundaries on the left, right, bottom, and up will be given. So we need to find the values inside. So that's a problem. Okay, so the method is going to be finite difference formula, finite difference equation that we need to find. We need to find this one in order to reduce this problem, which is given here, into a system of linear equations so that we can solve using the methods that we discussed in chapter 1. Okay, in order to use the finite difference formula, we start with something called central difference rules. We are going to eliminate this derivative, uxx and uyy. So what are they? Uxx is written like this. Uxx is ui plus 1j minus 2uij plus ui minus 1j divided by h squared. This is actually a second derivative that we discussed in the last video. Second derivative formula from central difference rules that we discussed in the last video. This is uxx. That means I is moving, j remains the same. For uyy, j is moving, I remains the same. Similar, quite similar. So instead of I plus 1, we have j plus 1 here. And instead of I minus 1, we have j minus 1 here. Instead of h, we have k. So we are going to use these formulas to derive the finite difference equation for the problem. Okay, now we discuss the example. So best to illustrate this problem through example. So we are given this equation, uxx plus uyy equal 500xy. So this is g, mentioned here. This is g. And then x is this domain here from 0 to 0.8. Y is another one from 0 to 0.3. H is given here, which is 0.2. K is given as 0.1. Okay. So with this information in the first sentence here, we should be able to draw the domain. The first step in solving the problem is to draw the domain. But before drawing the diagram, we need to know the number of intervals in the horizontal direction, n. So what is n? N is the last value of n, x, minus the first value of x divided by h. So 0.8 minus 0 over h is 0.2. So we get this one here, which is 4. So n is 4. The number of horizontal intervals is 4. Similarly, with m is last y minus first y, 0.3 minus 0 over the width, which is 0.1. So we get 3. So m is 3. So n is 4, so we can draw 1, 2, 3, 4. And then m is 3. So 1, 2, 3. So this is the diagram that we are supposed to get. So this is the first step in solving the problem. You should be able to draw the diagram correctly like this. If you draw wrongly, the whole thing will be wrong. Okay, next is to determine the boundary values. The boundary values are given here. U of 0, y is given as 15 sine y. So that means x is 0, which is this line here. The equation is 15 sine y. So for 15 sine y means we put in the values of y. The first value of y is 0.1. So we put here, so we get the first value, which is U01, is 1.4975. Okay, same thing. The second value, y is 0.2. So we put that into this equation. So we get 2.98. Remember, when you compute sine y, y must be in radian, not degree. If you put degree, you get different values, which is wrong. Okay, so we get these two values. Okay, next, the right values, the right boundary. So the right boundary, we have this equation given here. X is 0.8, which is this line here. So we put in the values of y, starting with 0.1. So we put in y equals 0.1 into this equation, we get this value. That is U41. So we get 10.858. When y is 0.2, we get this value by putting it into here. So we get 9.8248. Okay, left, right are given. Don't worry about the corners here. We are not going to use them. Okay, bottom values. So the bottom values down here is called initial value. Instead of calling it boundary value, it's actually initial value, but don't worry about that. It's just different terminology. So the values here is given as when y is 0, so it becomes a function of x. 8e of minus x is given here. So we put in the values there. When x is 0.2, put it here, so we get this value. When x is 0.4, into here, so we get this value here. When x is 0.6, into this equation, we get this value. Okay, done with bottom values. Above, on top, this is the equation given. When y equals 0.3, 10x. So when x is 0.2, we get 2. When x is 0.4, we get 4. When x is 0.6, we get 6, based on this equation. So we have the boundary values given here. So we have the boundary values computed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are all givens. We need to find these values, all this. How many of them? There are 6 unknowns. U11, U21, U31, 12, 22, 32 that we need to find. Okay, so that's a problem that we need to find. Okay, in order to find these 6 values, we need to find the finite difference equation. We need to find the finite difference equation. How to do that? We need to use this formula. These two formulas, uxx, uyy. Put them here, so we get this. So now, all x, all y, replace with, instead of x, we replace with xi. Instead of y, we replace with yj. Okay, because we make it finite. This is the finite thing in the problem. I and j, discrete values. Okay, so we have this. This is uxx, and this is uyy from these two formulas. Okay, now simplify. The rest is just algebra. Okay, find the common denominator, h squared, k squared, and put them on the right hand side. So we get this. H squared, k squared are the common denominator. So we multiply with the first term here with k squared. So we get this. And the second term, we reply with h squared, we get this. Okay, so we get this equation here. So what we do here is, once we have done that, once we have multiplied them, we need to group together terms that involve ui plus 1j, uij, ui minus 1j, ij plus 1, ij minus 1. There are 2 terms involving uij, one from here, one from here. So that's why we have this. Okay, you need to do a lot of practice on this. Okay, so this is what we get. So once we have this, put the values of h and k. H is 0.2, k is 0.1. Put them here. This is what we get. This is what we get. Okay, and then finally do this arithmetic. So we get the finite difference formula, which is this one here. This is the finite difference formula that we need very badly in order to reduce this problem into a system of linear equations. That will be in the next page. Okay, so we start here. This is the finite difference equation that we obtained just now. If we look at this equation, we can do a simple graph. We call it molecule. We call it molecule, where Uij is right in the middle from here. And then what are the players involved? I plus 1j, I minus 1j. I plus 1j is right here. I minus 1j is right here. Ij plus 1 is right up here. Ij minus 1 is down here. So make sure Uij is right in the middle, and they're they are connected through this diagram here. And then the coefficient we can put here. For example, Uij minus 0.1. Okay, then Uij plus 1, the coefficient is 0.04, and so on. So we can put that. And notice that if we have this diagram, we add up all these numbers, we should get 0. Okay, 0.4, 0.04, 0.04, 0.01, 0.01. That becomes 0.1. Then add with this one, we get 0. So the sum of the coefficients on the left-hand side should be 0. Okay, don't worry about that. So we discussed this one here, this one here. Okay, now we are ready to solve the problem. This is the finite difference formula that we obtain. Okay, in order to generate the solution, we start with I equal 1, j equal 1. Why is it 1 and 1? That's because we take this molecule, we put it in this diagram. So this is what we get. So I1, J1, that's a starting point. So this is the molecule, which is in star shape. So that means I is 1, J is 1. That's why we start with I equal 1, J equal 1. So we put it here. So we put I equal 1, J equal 1 into this equation. What happened? Into this equation, we get this. We get this one here. This one here. When I equal 1, J equal 1, we get this one here. Okay, looking at this equation, we know the value of fx1, we know the value of y1. Put the values there, so we get this. And then we also know the value of this one here and this one here from the boundaries that we computed just now, this one and this one. Okay, so put the values. So we have this and this, and these constants, we move to the right hand side, we get this. The rest remain on the left, so we get equation number 1, which is this one here. So finish with equation number 1. Okay, next we move the molecule, this one here, to the right hand side. To the right hand side in this diagram. So what happened? It's going to be I equal 2, J equal 1. So I equal 2, J equal 1 into this equation. What happened? We get this. So we get this. And we know the value of x2, y1, okay, which are this one here. And we also know the value of 2, 0, which is this one here. And we move this to the right hand side. We get equation number 2, which is this one here. So this is equation number 2. Okay, repeat with I equal 3, J equal 1. We get this equation. And we know the values of x3, y1. We know the value of 3, 0. Put them in, we also know the value of 4, 1. So we have this, and this one here, move to the right hand side. So we get equation number 3. We get equation number 3. Okay, so we don't have I equal 4, j equal 1 anymore because we have come to the end here. So we move up now from the left. Okay, so this time is going to be I equal 1, j equal 2. So I equal 1, j equal 2. So we get this. Okay, from here we know this value, and we also know this value. Put them in. We also know this value, so put them in and move these two to the right hand side. So we get equation number 4. So we get equation number 4, and then move to the right with I equal 2, j equal 2. We get equation number this one here. We get this one here, and then what do we know? We know the value of 2, 3. So move to the right hand side. Okay, we get equation number 5. And finally, I equal 3, j equal 2. We get this. And what do we know? We know this value, and move them to the right hand side. So we get equation number 6. We get equation number 6. So equation number 1, 2, 3, 4, 5, 6. In matrix form, this is what we have. We arrange according to U1, 1, 1, 2, 1, 3, 1, 1, 2, 2, 2, 3, 2. This is what we get. Okay, solve using the method that we know in chapter 1, Gauss elimination method or crowd or whatever, and we get the solution, which is this one here. So this is like 6 by 6 system of linear equations. It will take time to solve. In the exam, you will not be able to do it on time. So therefore, normally in the exam, if it is 6 by 6, you just leave the answer in this form. You don't have to solve the system to save time. Okay, so that's Poisson. So if we move to Laplace problem, we discussed Laplace. The difference between Poisson and Laplace is the right hand side here. If it is 0, we call it Laplace. That's the only difference. And the way we solve the problem is similar to Poisson. So we discussed this problem, this one here. We have the same boundary values. That means we don't have to discuss, in order to save time, we don't have to discuss detail how we get this diagram. It's come from the previous example. So this time, the only difference is the finite difference equation. It will be different because of this. So we do this, 0, 0, 0, and then we simplify. We get a different finite difference equation because of the right hand side 0. So we get this one here. Okay, so the way we solve the rest of the thing that we need to solve. So from here, same thing. I equal 1, j equal 1, so we get this equation. And then I equal 2, j equal 1, we get this equation. And then so on. So the final system is going to be this one here, which is slightly different from Poisson. And the solution will also be different. Okay, so study this one. So you need to know Poissons. That's the fundamentals. It's because Laplace just follow Poisson. Okay, thank you.